Hello friends, welcome to the presentation series We Will Overcome. This program is organized by Department of Physics, Sacred Heart College, Tevra under the guidance of Dr. Pius Augustine, Assistant Professor, Department of Physics, Sacred Heart College, Tevra. This lecture is presented by Ghanashyam Shekhar, myself Akshaya Sony, Parvathy U, Dona Lal and Steve Jo CM. The topic under discussion is a very familiar one. It is the fundamentals and laws of thermodynamics. Let's see the contents of the presentation. First of all, fundamentals of thermodynamics is handled by Ghanashyam Shekhar. The zeroth law of thermodynamics is presented by Akshaya Sony. The first law of thermodynamics is presented by Parvathy U. The second law of thermodynamics is presented by Dona Lal, and finally, the third law of thermodynamics is presented by Steve Jo CM. So without any further delay, let's move on to our topic.
Get fundamentals down and the level of everything you do will rise. A quote by Michael Jordan, American basketball champ. With this quote in mind, myself Ghanashyam is here to introduce you all to what exactly is thermodynamics and also some very important terms to build you more fundamentally strong to study the laws of thermodynamics. Let us begin by knowing what is thermodynamics. Thermo and dynamics. Thermo is a Greek word for heat and dynamics is the study of motion. So, literally it means motion of heat. And heat is used to refer energy. Since most common and easy way to understand energy is in the form of heat. So, why is it dynamics? Well, as in classical mechanics, when we study the motion of an macroscopic object, we consider things like displacement, velocity, etc., and how things are interrelated. Considering these factors, we make a full image of the moving object. In the same way, when we are studying thermodynamics, we are concerned with the flow of heat and the factors governing the flow of heat, which are pressure, temperature, volume, etc., and how these factors together create a picture of the flow of energy. This is the basic or the general definition of thermodynamics, but the core of thermodynamics lies in its laws, which will be discussed in the later parts of the presentation. Now let us know why is thermodynamics important. Thermodynamics has contributed a lot to human life. Some of these areas are that all processes which occur in nature and our daily life, these are guided by thermodynamic laws. Its applications can be seen in refrigerations, air conditioning, heat engines, etc. And also many units like boilers, fans, etc. are designed based on thermodynamic entities. Also, thermometer, which is an invention born from the thermodynamic laws. Now let us see the fundamentals of thermodynamics. Here we will be discussing the basic terms which could be helpful for you to understand the laws of thermodynamics. First, the system, surroundings and the boundary. System, the quantity of matter or region in space chosen for study. Surroundings, the mass or region outside the system. And boundary, real or imaginary surface that separates the system from its surroundings. That is, in thermodynamic analysis, the system is the object of investigation. A boundary is a closed surface which surrounds a system, and everything that is external to this is known as surroundings. Next, the types of systems. There are basically three types of systems: the isolated system, closed system and an open system. In isolated system, neither energy nor mass is allowed to exchange with the environment. That is, no interactions are possible at all, and these are completely closed off. Example is a coffee in a closed and well insulated thermos bottle. And in closed system, only energy can cross the selected boundary. Example is a tightly capped cup of coffee. And in open system, both energy and matter itself can be exchanged with the environment. Example, an open cup of coffee. Now, the concept of heat. As we all know that heat is a sensation of warmth, but this concept of heat is that heat is the form of energy that flows from higher temperature to lower temperature. That that means it's a form of energy that flows due to temperature difference. Now, the thermal capacity, it is the heat required to raise the temperature of body by 1 degree Celsius. And specific heat capacity is the amount of heat required to raise the temperature of unit mass of the material by 1 degree Celsius. Here unit mass has to be noted in specific heat capacity. Now the properties of a system. Any characteristics of a system is called as a property of system. These properties can be classified as intensive and extensive properties. Intensive are those properties which are independent of mass of system under consideration. Example, pressure, temperatures, etc. And extensive, these properties are those properties which depends on the mass of system under consideration. This is directly dependent on the mass of the system. Example, volume, energy, etc. A system is said to be in thermodynamic equilibrium if it is in thermal, mechanical, and chemical equilibrium at the same time. Let us understand these three equilibriums briefly. First, mechanical equilibrium. A system is in mechanical equilibrium when the net forces acting on the system is zero. It is basically the equality of forces or the no unbalanced forces. The second, the thermal equilibrium, where the system is said to be in thermal equilibrium if it has equality of temperature with the surroundings. That is, the variables are stable here. And in chemical equilibrium, it is the state when both reactants and products are present in concentration and have no further tendency to change with time, so that there is no observable change in the properties of system. It's the absence of any chemical reaction. And if any one of the equilibrium conditions is disturbed, then the system cannot be under thermodynamic equilibrium. Now let us see the types of processes. The operation by which a system changes from one state to another is called a process. And whenever a system changes from one state to another, it is accompanied by a change in energy. The change of state in such process is called a thermodynamic process. First, let us see the isothermal process. A process is said to be in isothermal if the temperature of the system remains constant during each stage of the process. The second, the adiabatic process. A process said to be in adiabatic if no heat enters or leaves the system during any step of the process. And in isochoric process, here the volume is remained constant. In any isochoric process, the work done by the system is always zero. The last, the isobaric process, here pressure is held constant during each step of the process. Now the adiabatic curve. The variation of volume of a substance with change of pressure under adiabatic conditions, this is represented by a curve, and this curve is known as adiabatic curve. And the isothermal curve, wherein the variation of volume of the substance with change in pressure in isothermal process but at a constant temperature. This represented by a curve is known as isothermal curve. The adiabatic wall is an insulating wall which does not allow heat to pass through it. And diathermal wall is just the opposite of adiabatic wall, which permits heat to pass through it. Now let us see some very important basic thermodynamic quantities. First, the internal energy, which is denoted by U or E. It is the definite amount of energy which is associated with every system. and enthalpy, denoted by H, is defined as a sum of internal energy of a system and the product of pressure and volume of the system. And the change in enthalpy is the sum of the change in internal energy and the work done. And the last, entropy, which is denoted by S. It is the measure of disorder or the randomness of a system. And an ordered system has low entropy and a disordered system has high entropy. That is, the greater the randomness, the greater is the entropy. With this, I conclude my part for the presentation on the fundamentals of thermodynamics. Thank you.
Hello friends, I'm Akshaya and I'm here to discuss about the zeroth law of thermodynamics. So let's move on to the topic. So the first thing I want to share is that why is it called the zeroth law of thermodynamics? The truth is that the other thermodynamic laws, the first, second, and the third, had already been named by the time the zeroth law was formulated. So we may think that why can't it be named as the fourth or fifth one? So the reason behind that is the idea shared in the zeroth law is more fundamental than the ideas shared in the other laws. So scientists thought that it should go before all the other laws and hence it was termed the zeroth law of thermodynamics. The name zeroth law was invented by Ralph H. Fowler in the 1930s, long after the first, second, and the third were widely recognized. Basically, this law frames an idea or concept of temperature as an indicator of thermal equilibrium. Now let's consider two bodies A and B. Let A be the hot one and B be the cold one. We know that heat flows from a hot body to a cold body. So here heat flows from A to B and after some time the flow stops. It is because both the bodies will attain the same temperature. That is, they are said to be in thermal equilibrium with each other. The term thermal equilibrium will help you to understand the statement of the zeroth law. The zeroth law of thermodynamics states that if two bodies A and B are in thermal equilibrium with the third body C, then A and B are also in thermal equilibrium with each other. Now, let's consider a figure. Here there are three systems, system A, system B and system C. System A and system C are in thermal equilibrium, which means that system A and system C will have the same temperature. Similarly, system B and system C are also in thermal equilibrium, which means that system B and system C will also have the same temperature. So from this we will get the point that system A and system B are also in thermal equilibrium with each other, that is, they also have the same temperature. Now I hope that you all understand the statement. Now let's move on to the explanation of this law. Consider the figure A and B. Both consist of an adiabatic wall. In the figure A, two systems A and B are insulated from each other, which means that they are not in good thermal contact, but they are in good thermal contact with the common system C. System A and system B will attain thermal equilibrium with the third system, that is, with the system C. Now in the figure B, the insulating partition is removed, that is, system A and system B are brought in thermal contact, and we find that there is no further change from the previous one. This means that system A and system B are also in thermal equilibrium with each other. So this is the zeroth law of thermodynamics. Now let's move on to the next topic. We can say that the concept of temperature was developed through the zeroth law of thermodynamics. We know that if the thermodynamic variables like pressure and volume are stable with the system, it is said to be in thermal equilibrium. Then there should be some physical quantity which is a function of P and V, that is pressure and volume of these systems. Let phi be the function and we will get that the physical quantity is temperature. Let's see how it came. Consider three fluids A, B and C. Let PA/VA represent the pressure and volume of A, PB/VB represent the pressure and volume of B, PC and VC represent the pressure and volume of C. From the statement of zeroth law, consider these situations. If A and B are in thermal equilibrium, phi1 PA/VA is equal to phi2 PB/VB. We know that phi is the function and this phi1 PA/VA represent a physical quantity and similarly phi2 PB/VB also represent a physical quantity. These two functions are equal if A and B are in thermal equilibrium. So we need to know that what is that physical quantity which is same when A and B are in thermal equilibrium. So phi1 PAVA is equal to phi2 PBVB, which gives F1 PAVA PBVB. We know that if there are four parameters describing the state, then any one of the four parameters can be expressed in the terms of other three. That is, PB is equal to F1 PA VB. That is, PB can be expressed in terms of PA, VA and VB. Let this be the first equation. Similarly, if B and C are in thermal equilibrium, phi2 PBVB is equal to phi3 PCVC, which gives F2 PBVB PCVC. From this we can write that PB is equal to F2 VB PCVC. Let this be the second equation. From the first and second equations, if A and C are in thermal equilibrium separately, we can write F1 PA/VA/VB is equal to F2 VB PC VC. Let this be the third equation. If A and C are in thermal equilibrium with B separately, then A and C are also in thermal equilibrium with one another. That is, F3 PA/VA PC VC is equal to 0. This is the fourth equation. From the third and fourth equations, we can write that phi1 PA/VA is equal to phi3 PC/VC. That is, when A and C are in equilibrium. In general, we can write that phi1 PA/VA is equal to phi2 PB/VB is equal to phi3 PC/VC. These functions have the same numerical value though P and V are different, and it is termed as temperature, that is phi PV is equal to T, and thus we understood that the physical quantity was temperature. This is known as the equation of state of fluid, and thus we can say that zeroth law defines temperature. So these are the few important things we need to know about the zeroth law of thermodynamics. Now let's see the uses and applications of zeroth law. The very first application is we can apply the zeroth law to compare the temperature of multiple objects. The second one is thermometer. We know that thermometer is a device used to measure temperature and it is an application of zeroth law of thermodynamics. Now let's see the limitation of zeroth law. Zeroth law just tells us about the equality of temperature. It does not give any clue how the heat is transferred. In overall, we can say that the zeroth law of thermodynamics is a consequence of thermal equilibrium and allows us to conclude that temperature is a well-defined physical quantity. So this brings me to the end of my presentation. Thank you.
Hey all, I am Parvathy. So far we have discussed about the basics of thermodynamics and the zeroth law. So next we are going to see the first law of thermodynamics that is very familiar to all of you. Before going straight to my topic, let me explain the conservation of energy principle. If we are interested in how heat transfer is converted into doing work, the conservation of energy principle is very important. So, the first law of thermodynamics applies the conservation of energy principle. It states that energy can neither be created nor be destroyed. The first law states that energy can be changed from one form to another, but it cannot be created or destroyed. In other words, the total amount of energy and matter is a constant. Next is the mathematical equation for the first law, that is, delta U is equal to Q minus W. Here, delta U is the change in internal energy, Q is the sum of all heat transfer, W is the net work done by the system. Next is the first law for some special processes. They are isovolumetric, isothermal, adiabatic. In isovolumetric, the volume is a constant, that is, there is no work done. In isothermal process, temperature is a constant, there is no change in internal energy. And in adiabatic process, the walls are thermally insulated so that there is no energy transferred as heat. And in isolated system, there is no energy transferred as heat, no work done, and no change in internal energy. That is, the equation delta U is equal to Q minus W for an isolated system become 0. Next is the examples for the first law. We know that physics extends well into our everyday life. So, here are some examples for the first law. Look at the picture of the ice cream. The ice cream, when we consume, the internal energy is converted into kinetic energy when we ride a bicycle. Similarly, the light energy provided by the sun is used by the plants for photosynthesis. Next one, the light bulb transform electrical energy into light energy is an example for the first law. Next similar example is that just consider when we are in a room of full people. After some time we will start sweating and we will feel warm, isn't it? And the sweating becomes excessive if the room size is small. This happens because our body is trying to cool off, hence, heat transfer from your body in the form of sweat. This entails the first law. Similarly, the handles of bicycle pump will be hot due to the mechanical work done to increase the internal energy. These are so familiar, that is, these are the examples for the first law. Next, we are going to the applications of the first law. We had said that the limitation of the sir of the law is that it doesn't say anything about the heat transfer. So, this limitation is corrected in this law, that is, the heat transfer from high temperature to low temperature. And the heat engine cycle, including auto, diesel, etc., work under the first law. The laws of thermodynamics are simple to state, but it has a wide range of application in everyday life. Next is the significance of the first law. It introduced the concept of internal energy. It helps to determine the change in internal energy, that is, delta U can be written as U2 minus U1, that is, final internal energy minus initial internal energy, and it is applicable to any process that undergo physical and chemical change. Next is the limitations of first law. It says about the heat transfer, but it says nothing about the direction of flow. And it says nothing whether the process is spontaneous or not. Reverse process, that is heat transfer from lower temperature to higher temperature, is not possible with this law. That's all about my topic. Thank you.
Second law of thermodynamics. As we have seen, the first law of thermodynamics posed some limitations. So, in order to overcome these limitations, the second law of thermodynamics was introduced. It states that the total entropy of an isolated system never decreases. We know that in an isolated system there is no transfer of mass or energy between system and surroundings. Hence, the system will be in thermodynamic equilibrium having maximum entropy. The second law of thermodynamics clearly explains certain limitations posed by the first law. They are: it explains the direction of flow of heat, the feasibility of a process. It also states that energy cannot be completely converted into equivalent work. Now let us see what is entropy. Entropy is defined as the degree of randomness or disorder in a system. Or in other words, it is the amount of energy which is unavailable to do work. It is represented by delta S equal to delta Q by T, where Q is the amount of heat and T is the temperature. Now consider two processes, that is reversible process and irreversible process. In a reversible process, the entropy is constant. It is because in this process there is no transfer of heat or energy. But in case of an irreversible process, the entropy increases. Mathematically, it can be represented by the equation delta S universe is equal to delta S system plus delta S surroundings, which is greater than or equal to 0. Here delta S universe is the change in entropy of the universe, which is the sum of change in entropy of the system and change in entropy of the surroundings. From this mathematical equation, it is clear that entropy can never be decreased, it is always greater than or equal to 0. Coming to the next topic, reversible and irreversible processes. Before going to the distinction between the two processes, let us consider a thermodynamic process. In this process, it goes from an initial state to a final state. It also involves the absorption of heat in order to do work. So, while considering the case of a reversible process, both system and surrounding return to their original state or the initial state. But in case of an irreversible process, both system and surrounding does not return to their original states. The name itself suggests it is irreversible. Next, in a reversible process, it is quasi-static. It means that the system is in thermodynamic equilibrium throughout the process. But in case of an irreversible process, it departs from the equilibrium. Reversible process is a slow process, whereas irreversible process is a rapid process. Next, there are two statements that explain the second law of thermodynamics. They are Kelvin-Planck statement and closure statement. So first, let us see what is Kelvin-Planck statement. According to this, it is not possible to convert the energy completely into work. That is, heat engine cannot have the thermal efficiency of 100%. It is because during the conversion, some amount of energy is lost in the form of heat. The picture clearly describes the statement. It says that no heat engine can have a thermal efficiency of 100% by converting energy completely into work. Next is closure statement. According to this statement, heat cannot be transferred from a colder object to a hotter object unless an external work is done. From the figure, it is clear that an external work is done to the system in order to transfer heat from a body of low temperature to a body of high temperature. Now, let us see what is a Carnot cycle. This cycle was proposed by a French physicist, Sadi Carnot, in 1824. So, what led to this proposal? He had some questions in his mind, which led to its proposal. He considered two reservoirs, that is, a hot reservoir and cold reservoir. He considered the question of what is the maximum efficiency possible for a heat engine to operate between them. He also thought that how can we attain this maximum efficiency? These questions led to the proposal of Carnot cycle, which in turn led to the discovery of Carnot engine. So, a system undergoing a Carnot cycle is called a Carnot heat engine. A Carnot heat engine is a reversible heat engine that is operating between two temperatures, T1 the source and T2 the sink. There are four stages involved in a Carnot cycle. The first one is reversible isothermal gas expansion. The second one is reversible adiabatic gas expansion. The third one is reversible isothermal gas compression. And the last is reversible adiabatic gas compression. This figure shows the diagram of a Carnot engine. Now let us see the four stages involved in a Carnot cycle. The first one is reversible isothermal gas expansion. Here, the heat is transferred reversibly from high temperature reservoir at constant temperature Th. We can see a hot reservoir, a cold reservoir, and ideal gas particles within the system. So, heat is transferred from hot reservoir to the part of the system which contains ideal gas particles. The heat is absorbed by the ideal gas particles and it expands, which results in the upward motion of the piston. As a result of the absorption of the heat, the temperature of the system increases. Next is adiabatic gas expansion. Here, the expansion of gas continues. As a result, the ideal gas particles tend to cool down, which results in the decrease of temperature of the system. The next is reversible isothermal gas compression. Here, heat is transferred reversibly to low temperature reservoir at constant temperature Tc. The temperature within the system remains same and the surroundings continue to do work on the system, which causes the piston to move downwards and causes compression. The next is reversible adiabatic gas compression. Here, no exchange of heat takes place and the piston return to their original state. In this stage, the temperature of the system increases. So, this shows the work done by gas in a Carnot cycle. As we have seen, there are four stages involved in a Carnot cycle, and these equations give the work done in each cycle. In isothermal gas expansion, work done is nu RT log V2 by V1. In adiabatic gas expansion, work done is given by nu R into divided by gamma minus 1 into T1 minus T2. In isothermal gas compression, work done is nu RT log V3 by V4, and in adiabatic gas compression, work done is nu R by gamma minus 1 into T1 minus T2. This shows the PV diagram of a Carnot cycle. Here it shows isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. The x-axis shows the volume and the y-axis shows the pressure. Now let us come to the last topic, that is efficiency of a heat engine. So, Efficiency is the maximum efficiency a heat engine can obtain. Here, efficiency is given by 1 minus Q2 by Q1, or it can also be represented by 1 minus T2 by T1. The efficiency of a heat engine is given by T1 minus T2 by T1. As T2 increases, T1 increases, and hence the efficiency of the engine increases.
So far, we have seen the three laws of thermodynamics. The next is the third law. The third law of thermodynamics was proposed by Walter Ernst. This law mainly deals with the concept of absolute zero. So, before stating the third law, we must know what is absolute zero. Absolute zero is the lowest possible temperature. And by definition, temperature is the measure of heat energy, that is, kinetic energy in motion. When temperature decreases, the internal energy and the kinetic energy of the system decreases. If we keep on decreasing this temperature, a point will be reached where there is no kinetic energy. At this point, there will be no temperature by the definition. This condition is called absolute zero. So, the third law of thermodynamics states that the entropy of a perfect crystal at a temperature of 0 Kelvin is equal to 0. So, to prove this law, we have an equation called the Boltzmann's equation. S is equal to Kb log W, where S is the entropy, Kb is the Boltzmann's constant, and W is the number of microstate. At absolute zero, the number of microstate will be equal to 1. So by substituting it, we will get S is equal to Kb log 1, where log 1 is equal to 0. So we will get S is equal to 0. Hence, the third law of thermodynamics is proved. The main importance of this law is that it helps to calculate many thermodynamic properties like internal energy and entropy. It helps to study the behavior of solid at very low temperature, and it also helps to analyze the phase and chemical equilibrium. The main limitation of the third law is that certain crystals of carbon dioxide, nitrous oxide, and water do not have a perfect order even at absolute zero. That means the number of microstate is not equal to 1. So the entropy is not equal to 0 at absolute zero.
Let us recap what we have discussed. Initially, we have seen the introduction which says what is thermodynamics and why is thermodynamics important. Then we came across the fundamentals of thermodynamics, types of system, properties of a system, and also thermodynamic quantities involved in a thermodynamic processes. As we have seen, there are four major laws of thermodynamics. They are the zeroth law, first law, second law, and third law. From that, first we have seen the zeroth law. It states that if two bodies A and B are in thermal equilibrium with the third body C, then A and B are also in thermal equilibrium with each other. We have seen the explanation of the zeroth law, its uses, applications, limitations. Then we came across the first law, which states that energy can be changed from one form to another, but it cannot be created or destroyed. We have also seen the explanation and examples regarding the first law. We also discussed the applications as well as the limitations of the first law of thermodynamics. Then we came across the second law of thermodynamics, which states that the total entropy of a system never decreases. We have seen the Kelvin-Planck statement and the Clausius statement, Carnot cycle, and efficiency of a heat engine in the second law of thermodynamics. Next, we came across the third law, which states that the entropy of a perfect crystal at a temperature of 0 Kelvin is equal to 0. We have also seen the proof of the third law and also the limitation. Thereby, we conclude our presentation. Thank you.